Okay, question 10 is a proof question. It says prove that for all values of n, so all natural numbers this means, so that's the integers, that n squared plus 2 is not divisible by 4. In order to prove that, we need to, well, we need to think about what type of proofs we have available to us and what would or wouldn't work. We've got proof by counterexample. That's not going to work here because we need to prove it for all values, that all values aren't divisible by 4. We've got proof by contradiction, which again wouldn't work because it's for all values. So the only other thing we're kind of left with is the ones where we check odd values of n and even values of n and show that it doesn't work for both cases. So if we look at the case for when n is even. When n is even, we can write n as two lots of any number where k is a natural number. When we substitute that into n, we get 2k all squared plus 2, which multiplies out to 4k squared plus 2. So we've got a multiple of 4 here, but then we're adding on 2, which won't be a multiple of 4, because we've got a multiple of 4 plus a number that's not a multiple of 4. So this won't be a multiple of 4, as 2 isn't a multiple of 4. So if we do the same thing now for when n is odd, then we've covered all numbers. Remember, 0, if you're thinking about 0, 0 counts as an even number. 2 lots of nothing is nothing, so that's accounted for in here. So when n is odd, we've got that n can be written as 2k plus 1, again where k is any natural number. And then if we square that, we are going to get 4k squared plus 4k plus 1 plus 3. Plus 2, sorry. Let's get ahead of myself. Which simplifies to 4k squared plus 4k plus 3. And this is a multiple of 4. We can take that factor of 4 out here. But then we're adding on a number that's not a multiple of 4. So we've got a multiple of 4 here. But then the 3 isn't. So again, it won't be a multiple of 4 because 3 isn't a multiple of 4. Okay, so it doesn't work for any odd or even number, which means it's not for any odd or even integer. Okay, part 2 says that x is any real number, so it can be a decimal, it can be a fraction, it can be an irrational number. The value of the modulus of 3x minus 28 is greater than or equal to the value of x minus 9. State with a reason if the above statement is always true, sometimes true, or never true. Anytime you see a modulus function, especially when you've got a linear function inside the modulus, I reckon the best strategy for these is drawing, or sketching I should say, the graph of the function. the 3x minus 28 graph is going to be a straight line, one of the standard modulus function graphs, but it's going to have a gradient of 3. So even though this doesn't really look like it's got a gradient of 3, I'm going to make it have a gradient of 3. It's going to intercept the y-axis at 28 and it's going to intercept the x-axis at 28 over 3. The x minus 9 graph has got a gradient of 1 and intercepts the y-axis at negative 9. So that's going to look, if I use another colour, something like, well, we don't actually know for sure. It might look like this, or it might look like this. It's not gonna be steeper because we know the gradient's only 1 and the gradient of the blue line is 3. So we know it's going to be shallower than this line, but how shallow? Without drawing it accurately, we're not sure. So what we need to know is we need to know where this graph crosses the x-axis. That's going to be quite useful. So whether it's before the 28 over 3 or after the 28 over 3. So it crosses the x-axis. Well, it's quite easy to work out. It's going to cross the x-axis at 9. So if I mark minus 9 on here, this is going to cross the x-axis at positive 9, and 28 over 3 is just over 9, 9 1/3. So it's going to cross the x-axis just before the blue line, which means it's going to look like this. And that's really, really important to see that it's going to cross the blue line twice. Because that now shows that in this little section here, whatever those numbers are, x minus 9 is actually greater than the modulus, the 3x minus 28. So the answer to the question is that it's sometimes true. And the reason it's sometimes true is because when x is less than whatever this value is, which we could work out, well, let's work it out. 3x, well, it's going to be minus, this line is the negative version of the 3x minus 28. So it's going to be minus 3x plus 28 is equal to x minus 9. We're going to get minus 4x equals minus 37. So x is going to be 37 over 4, which is 9 1/4. So we can say that when x is less than 9.25, the modulus function is greater than x minus 9. But in this region here, when x is between 9.25 and whatever this number is, so let's find that number out too, which is going to be 3x minus 28 equals x minus 9. So that's going to be 2x equals 37. So x is that right? No, it's going to be minus 9 plus 28, so that's 19, sorry. Um, 19 over 2 is 9.5. So the graph's really inaccurate, but what's important is that this value is 9.5. So whilst x is between 9.5 and 9.25, x minus 9 is the one that's bigger. It's above it. The orange is above the blue. So it's sometimes true when x is less than 9.25 or greater than, now we can add 9.5, the 3x minus 28 modulus function is bigger, but when it's between these two numbers, x minus 9 is the bigger one. So the statement is sometimes true. Now, you could have answered this question another way. You didn't actually need to draw the graph if you didn't want to. The other way to prove a sometimes true question is to find a point when it is true and a point when it isn't true. So you could have gone, well, look what happens when x is 8, and then look what happens when x is 9.4, for example, and that would have shown that when it's 8, the modulus function is bigger, but when it's 9.4, the modulus function is smaller. So that would have also worked for a sometimes true question.